There's three things that Siemens provides, and it's something you got to get used to when if you decide to take the certification test to help troubleshoot and understand the flow. So y'all understand the flow or the sequence of events that a line is supposed to make. If you don't understand the sequence of events or the operation or the flow that something goes through, then it's going to be highly unlikely that you'll be able to figure out what's wrong with it.
Now I was thinking about the sequencing. Would it be easy to create sort of like a ladder diagram?
Well, what we're going to do is we're going to use three diagrams. We're not going to worry about ladders. We use three diagrams, and this is what Siemens covers and uses on their test. And if you can understand these, and you have these charts, then these tell you exactly the sequence that the line should go in. First of all, we have what we call a step chart. As soon as this loads up, if it loads up. That work over here is kind of touchy sometimes. It might be a little harder in this lab because the access point is actually over in the other lab over there. That's pretty good. This is a pretty good size PowerPoint. Load up the module which I will be using, but what this is okay. So we went over the diagrams, we went over the symbols, basically the electrical and the pneumatic. Y'all have any questions on those so far? This is what Siemens refers to as step up. So what we do on the left is we put all the actuators. So we know everything consists of a circuit, right? So a circuit has a load. It has a source of power, and of course here we're using pneumatic power. And then normally we have, so we know the minimum makeup of a circuit, and that's a power source, a load, and conductors. Usually we have a power source, we have some type of control element, right? You understand? Control element, how we can control the power, the flow of energy. And also we have a load. So every one of these circuits, so this would be a circuit, and of course what we're doing for loads is we have these actuators, right? And here the load is actually not a true actuator, but it falls into the category of a load. So when we looked at the symbols, we learned A means actuator, and what does an actuator do? An actuator is a device that converts power into motion, okay, or energy in the motion, or pressure in the motion would probably be more correct. So this is not really, this guy right here is not really true, but this still falls into the category of loads. So we have 4 loads in this thing, right? And something's going to happen with those loads. Then here we have the control, right? And here we have the pressure source. And of course, here we're using pneumatic pressure. So these actuators are turning that pressure source of pressure into motion. Except this one. This is kind of different. So what we do on a step chart is we start off by setting up a grid. First of all, we figure out the number of steps. Here they say this has 11 steps. And then after 11, we go back to what? So it says 11 equals 1. And so most automated machines that I've ever been around runs through a cycle. So it starts, it does something, and then it goes back to the start and does it again, and it goes back to the start and does it again, right? And that's what automated manufacturing is. So what we do on the left is do what? We set it up. The grid depends on the number of vertical lines you have in the grid depends on the number of steps. The number of horizontal lines depends on the number of actuators. That makes sense. So we have 4 actuators. Okay. We have the part feed cylinder, which is actuator 1A. We have the vacuum gripper, which is 2A. We have the pickup cylinder, which is 2A. And we have the linear traverse cylinder, which is 4A. Okay on that? And notice, then we put what they can do. So here, what can it do? It can extend or retract. The vacuum can either be what? In or off. And then all our cylinders are either going to extend or retract. So when we start off, we go over there and look, and we see 1A is what? From the start, it's what? It's retracted. The vacuum is what? Off. Right? Cylinder 3A is what? Retracted. And then the traverse cylinder is retracted, but it's across this way, but it's to the left. So if you wanted to, you might put left, right. Here they put what? They put extend and retract, right? You understand that? Probably more correctly would be left, right. When the cylinder's mounted horizontally. All right, does that make sense? And then we come up here. What does it need right here to move? It need 1B needs to be what? It looks for what? 1B to turn on. Pressure switch is still what? Off. This is still retracted. This here. Then what happens now? Then we extend it. What happens? 2B becomes true. I'm sorry. 1B2 becomes true. Right? We follow this down. The gripper is still what? Off. When 1B2 becomes true, then what happens? Becomes true, and what does it do? It extends. Right? Does that make sense? Okay. And then we fall into this step. So what happens in step 3? Well, this guy here is still what? Extended. Right? You understand? This guy right here all of a sudden does what? Turns on. Right? You understand? This guy does what? Extends. And this guy right here is still retracted. So y'all see how this thing is laid out. And it's pretty neat. So what we got is we got a graphical, and of course we are visual species. So here we're actually getting a visual indication of what happens on all the steps. So that's what we need to do when we develop a step chart is we need to do what? First of all, we need to cycle that thing through. Count the number of steps. And that would determine what? That would determine how many vertical lines we have.
So this is how you want to draw it?
Yeah, this is the way they do their step chart.
So this is Siemens way of
Graphically indicating the sequence of steps. A section of a line will go through. And of course, what you'd have to do is you're going to have to divide it into section of lines. Every automated system I've ever been worked on has basically got different sections. And each section is responsible for doing something different. So number 4 galvanized line, we had the feed in, right? Then we had the welder that welded the strip together. Then we had the looper cars. We had the cleaning section where they came in and dipped it and ran it through all those acids to make sure there was no goop on it, so that before they. Then we had the preheat. Then we had the coating section. Then we had the cooling section or the tempering section. So every one of those was divided into different sections. So yeah, you'd have to do this with a step chart, because if you didn't, if you tried to do the whole line, even Mercedes, if you work at Mercedes, it's actually in different sections. You have the paint section, they do this, they do this, and that way, and then you can subdivide it. So, when you move into the robot station, when you move into the assembly station where they actually put all the parts together, weld them together, they go through like 6 different stations. Every station will have its own law, will have its own step chart. So this is called a step chart. Now the other method they use is what's called a function chart. Nope, okay. this guy, which basically is the same thing. So notice what we do on the left. We say, okay, what's required to start the thing? So what do we have to require?
Start.
So input, so what we do here is actually give the PLC, so this is input. Now I need to look at that. 'Cause that's
PLC addresses.
Yeah, then it's 4B1, this has to be true. So if the arrow points up, it means it's got to be true. If the arrow points down, it means it's got to be false. And then what do you have to do at the last? Press the what? Start. And then it sequences through. Okay, so step 1, I forgot what the N is. I'll have to go look. This would be Q4. So Q is what Siemens uses for the outputs. This is one thing I like on the, and I do it not often anymore, but a lot of people hit that 0 key for that O on the Allen Bradley PLC. So Allen Bradley uses O for output and I for input. Siemens uses I for input to identify an PLC input, and it uses Q to identify a PLC output.
So the PLC address is actually I1.3, line 1.
Yeah, these are inputs. So inputs are on the left. Yeah, so this would be.
Oh, I thought the input would be on the inside there.
I'm sorry, you're right. I need to look at this. Oh, these are
Steps.
Yeah, I need to go back and look at this, guys. Yeah, this is the input right here. Input 1.3, which is kind of, Allen Bradley does what? They put I and they put a colon, and then they put a module number, and then we either put a dot to specify 16 word, right? You understand? Or they put a what? They put a slash to specify it.
It looks like they're reference. So you see where the outside on the right side, like at the very top, all the way over, is 1B2.
This is the sensor.
And then you notice it go back over, like in between what he was just talking about, the 1.1, 1B2. Is this what it's like? It's reference to that?
What's this? What are we talking about? This?
No, she's talking about the
It
very
looks like-
inside, right there.
This is the sensor.
I mean, it goes to this, goes this, and this what it looks like.
Yeah, well, they say this guy here, this causes 1B2 to become true.
Mm-hmm.
Okay, this guy requires 1B2 to advance on. Does that make sense? Yes or no? So this causes 1B1 to become true. Then of course this needs 1B on. This needs 1B2 to advance to step 2. Y'all understand? Huh? Understand? So if we looked at the cylinder, we see that the cylinder has 2 sensors on it, right? 1B1. So what happens is that when this thing extends, 1B2 becomes what? True. What does this require? 1B2. This requires 1B2 to go to step 2. This causes 3B2 to come true. This requires 3B2 to be true before it moves to the next step. Okay, understand? So what does that mean? Well, what if the cylinder extends and everything stops? Odds are we would think about 1B2, right? You understand? Even back here on the step chart. So we come over here, this guy right here extends, and then it stops. Well, we'll see. This is what's required for that to become true, right? You understand? So either if we use the step chart or the function chart, each one of those tells us what's required to go. It tells us the results of the motion, and then it tells us what's required to go to the next step. Y'all understand? So what we could do is we could come down here and we could look at this and see where it stops at. So let's say it stops right here. Well, let's say, okay, so what should be true? 3B1, okay, or somewhere if we over on our step chart and it stops right here. Then what are we looking for? 3B1. See, so both of these, no matter which one I use, if all of a sudden it stops and I understand the sequence, but I've got to understand the sequence. If you don't understand the sequence of the way the line works, then there's no reason at all to go out there and even work on it. Right? You understand?
So you're saying like if it stops at 3B,
It'd be like trying to fix a car if you don't know how to crank it.
if it stops right there where you just drew the line, you look, make sure 3B2 is false, 3B1 is true, correct?
Well, this would be, we got this far right here. So what we would do is we would make sure this guy right here is indicating it's what? Retracted, right? And this guy right here, so 3B1 should be true, and 3B and what? So this should be, this would be your problem right here. So I told you this would be probably the problem right here. Oh, I'm sorry, it stopped right where? Right there.
But
Then this guy would be the one
if
with
3B2 is not going to fall, would they also stop it? For whatever reason?
yeah, and that's what we that's what we might look at. So this would be the first guy we would look at, right? You understand? But it's going to be yeah. And I don't know exactly what the PLC looks at. If 3B2 if 3B2 wasn't working, if it didn't go false, then we would have to understand the actual PLC program. Understand? Because this guy right here, once it sees 3B2 true, then it's going to be real hard for it not to be, unless it falls off or something.
Right, I mean, that's
Yeah.
what I'm saying. Yeah.
So these guys here, if you looked at the cylinder, these guys are bounded right here.
I guess.
It could be defective, but if it's defective, then we would never probably get started.
Well, I mean, I didn't ask it correctly. I guess what I was meaning to say, would the condition for 3B2 have to be false in order for it to move on, or does it disregard that and just look at 3B1?
Well, if 3B2 had to be false, then odds are it would stop right here. That makes sense? Well, if 3B2 went true and then stayed true, and then when it moved, then, I mean, see, if 3B2 was always true, understand what we're saying? Then what Mitchell says is we wouldn't get that far right here. Because what has to, yeah, because so 3B2 is not, according to the step chart, 3B2 is not looked at because it to do what?
It's looking for 3B1.
Yeah, it's looking for 3B1. So the PLC would be looking for 3B1. What would happen though, as soon as 3B1 went false, it would say that the thing was extended. And what would happen is that this step right here would move over here. It would try to do this step and that step at the same time.
Well, the reason I was asking, we had a situation last week where conveyor lines, it's got rock sensors. The metal pallets carry the engines, and it's got rock sensors in between the rotors on the conveyor. Well, that rock sensor has got to see metal, or it senses metal, it stops. Well, when the rotor starts up, the pallet's supposed to move upward. Somebody went there and placed washers on 3 of the sensors over the weekend. And those sensors are not, they're not really accessible where we can go in there while the line's running and try to figure it out. It took us a good 20 or 30 minutes to realize what was going on. We couldn't look at the VFC program. We just had to go up there and physically see what we could figure out. And that's the reason I was wondering if the PLC would not let it advance if the condition did not change. Because I know it's focusing on 3B1, but the 3B2 didn't matter at that point.
I don't know. I mean, that's something we would have to, that we would have to. So what you're doing is asking a question that you would not answer unless you came over here and looked at the actual PLC program,
So
right?
we're not allowed to do that.
But the problem is, you know, if it stopped right here, then you know you've got 3 sensors that could be causing the problem. Well, actually 4. This would probably be the most likely one. So what you would do is this is where you would probably start at, right? And then of course, what would we do then? We wouldn't move forward from that.
So then that's what we did. We looked at one that.
Now we wouldn't move forward from that, but we might move backwards because 1B1 is required for it to do this, right? You understand? So what that means is if 1B1 fails, then of course the thing would never retract. If this failed, then the thing would never move because now it can't get pressure. If this thing failed, then the pressure would never come on. So what would happen if this was on all the time, then odds are your vacuum pressure would come on instantly because that's all it's probably looking for.
Now, am I in the right mindset? Would we not do the same thing with that conveyor system? I mean, it's not cylinders, it's individual proxies. Would they not be?
Well, it's an actuator. It runs a motor. A motor is an actuator. But usually when we talk about motor, we're talking about something that can run more than 360 degrees. That's just a term. But a motor is an actuator. A motor is what's taking pressure, electrical pressure, and turning it into motion. So anything that takes electrical pressure and turns it into motion is going to be an actuator. It's just that usually when we use the term motor, we mean what? Yeah. When we use the term actuator, we mean it's either a linear actuator or a rotary actuator. Usually when we use the term rotary actuator, it's something that's less than 360 degrees. And then over 360 degrees, we usually say motor. So yeah, I mean, that's exactly what's happening. But odds are if 3B2 is defective, if it's on all the time, then this guy right here is depending on 3B2. So what would happen is your vacuum would come on instantly. It would stay on. Yeah, if it was messed up. Does that make sense?
Yeah, we was quite aggravated on that last week.
Yeah, it makes you wonder why they did that. You know, I bet it.
I like this line on.
Well, it was during shutdown, and not to be mean or whatever, I'm really surprised any of those guys were smart enough to do something like that.
Probably figured that.
Well,
Yeah, they was working with somebody.
Those sensors on that conveyor. Like I said, they're underneath, and I guess there's a sonic or whatever where it detects, but it has to be met. And which one? They just went there and sporadically placed washers on certain ones.
And it might have been somebody sabotaged them.
Well, that's kind of what we figured. We figured somebody was trying to delay startup.
We'll get some overtime.
This is a new chart. I really like this one. This is the actual PLCs. So this gives us a really, really good indication of what outputs and inputs are supposed to be true to start something. So right off the bat, if it won't start, if I had this chart, I could do yeah, I could go down through this list and see, okay, what's required to cause it to start? Well, all these right here are required to start. So right in here, I know input 0 has to be a what? 0, 1, 1, 0, 1, and I really like this chart.
We can do any one of those.
Well, not today. What we're going to do today is we're going to do the what? We're going to try to do the step chart. Now it's either right or wrong. Don't worry about that. All we're going to do is just see if we can try to develop that. We'll try to do a function chart. And then that's what we're going to try to do today.
So according to that, it does not look at every sensor.
No. Yeah, so here, this guy right here would make no difference. These are what we call don't care. That's a don't care. So the PLC program doesn't look at that. And they're not going to do that. You know, they're going to, so here it says the receive part, push button start, it's got to go, it's got to change states, what they're saying. And then it starts. Feed fully, then so only thing it's looking here to receive a start input. I mean, why would it be looking at the other sensors to receive a start input, right? You understand? So all it's sitting there right off the bat looking for one button. What button is it looking for? It's looking for a start button. So we press the start button, and then we do then we release.
So there's some systems out there. The little display reads system check or system pre-startup, something other message. Could it be that they're looking at the other sensors to make sure they're all in there?
It would be for this right here, for pre-startup, if it had a message up there, which would be neat. It would come up and tell you right off the bat which problem you had. Now, the more complicated they make a system, the more expensive it's going to be. Okay, y'all understand that? So what they're going to go between, they're going to go between feedback, non-feedback, or open loop, closed loop, and they're going to decide which one is required to do what. It's just like when the robot goes over there and we reset it and it goes up there and puts a spring down there, it has no idea another spring might be down there. Right, understand? And we do this on the Festo line too. The Festo line, if there's not a piston over there, if there's no sensor over there, the robot will spin around and go over there and what? Open its grip or go down there and clamp down and come over. It's up to people to decide when they put these things together where the sensors are going to be and where the sensors aren't. I like this chart right here. In fact, I like all of them.
I like that.
The function chart. Step chart. And what happened when we was at the training? It turned out that some people like the step chart, some people like the function chart better. Okay, some people like the function, and that's why we learn how to do both of them. Right? You understand? And if you got something like these, this would not only get you familiar with a system you didn't know how operated, because this tells you exactly the sequence of steps. So even if you went into a situation where you were new to this place, these guys tell you what to expect, right? You understand? It wouldn't be long at all. The learning curve would be very short on learning how that section of the line works. Are we okay? So it makes sense. So what we're going to do today is that's what we're going to work on. We're going to go over there, and I wish I had another air hose. I would like to be